All right, well, welcome to the Chapter 4 lecture. Chapter 4 is on gravity, projectiles, and satellites. And we're going to start today's lecture with someone that we're pretty familiar with already. We had a whole chapter on him in Chapter 2 with Newton's laws of motion. Now, the discussion of gravity usually starts with Isaac Newton because it usually goes back to the legend of the falling apple. Now, this story is a little bit questionable in authenticity, but it does provide a good starting point for maybe describing what Isaac Newton's thought process might have been when he was defining his universal law of gravitation. So, if you've ever seen a picture of Isaac Newton, oftentimes he is sitting under an apple tree. Sometimes the apple is falling near him, sometimes it's bouncing off his head. Usually see that one quite a bit. But the way the story goes is that Isaac Newton, who was a physics professor, was sitting outside studying or reading and sitting under an apple tree when an apple fell to the ground. And that got Isaac Newton thinking. He started to wonder, well, why did that apple fall? And why does the apple fall in the way that it does? Why does anything fall in the way that it does? So he might have thought, well, this is because the stem could no longer hold it to its branch. But that's not really good enough because what makes it unstable? What makes the stem not be able to hold it anymore? And then he might have thought, well, it's because the apple is heavy. And that was getting closer, but it still wasn't explaining why the apple fell the way that it did and what gave that apple weight in order to make it heavy in the first place. So Isaac Newton thought, and eventually what he came up with is the fact that all objects with mass draw other objects with mass towards each other. The more massive an object is, the harder they draw objects towards each other. The closer two objects are together, the harder they draw as well. So Isaac Newton thought if this process of objects with mass drawing each other closer to each other extends out to the highest apple tree and the highest apple tree in the orchard, and then out to the highest mountains on Earth, why would it not extend out even further? Maybe the reason that we orbit around the sun is because of this new force, which he defined as gravitation. Maybe that's why the moon orbits around the Earth. And eventually, that's the conclusion that he came to. This fact of all objects with mass drawing other objects towards each other is the reason for the apple falling. It's the reason that we stay on the Earth. It's the reason that the moon orbits around the Earth and the Earth orbits around the sun. So this theory is something that he called his universal law of gravitation. Now, it's often misstated that Newton was the first one to discover gravity, and that's not quite the case. Galileo, who was born in the same year who died in the same year that Isaac Newton was born, so much, much earlier, Galileo had discovered that all objects fall at a constant rate towards the surface of the Earth, that 9.8 meters per second squared quantity that we defined in an earlier class. So gravity in itself had already been discovered. What Isaac Newton discovered is that this property, this gravitational force, is a universal concept. So what that means is that you can use the same gravitational force equation to figure out the gravitational force between the apple and the Earth, or the sun and the Earth. It doesn't matter the size, it doesn't matter which objects you're defining. As long as you're defining two objects with mass, you can figure out the gravitational force between them using the same equation. This this discovery of this universal law of gravitational force kind of put the nail in the coffin for the geocentric theory, which was still hanging around, lingering at that time of Isaac Newton. The geocentric theory stated that the Earth was the center of the solar system, and all other objects in the solar system orbited around the Earth, including the sun. But we always knew that the sun was a lot more massive. It was much, much larger than the Earth. So once this came to fruition, that the more massive an object is, the harder it pulls other objects towards it, then it could no longer be that the Earth was the center of the solar system because the sun was so much more massive. The sun is the most massive thing. It contains about 98% of the mass of the solar system. So it pulls all other objects in the solar system towards it. And that's why everything orbits around the sun. All right, so that equation that I referred to is shown on this screen. The universal law of gravity, Newton's universal law of gravitation, states in words that every body in the universe attracts every other body with a mutually attracting force. And in equation form, that is shown on screen. We have F subscript G, which stands for the gravitational force. We're going to have a couple more forces in this class. We were introduced to the basic form of the force equation with F equals ma, and now we're going to define specific forces by adding a little subscript letter. So this was, you can tell it's a force because of the F, and then the G shows that this is the gravitational force. That is equal to the gravitational constant, which is 6.67 times 10 to the negative 11. Note that this is capital G, not lowercase g, which was our 9.8, the acceleration of gravity on Earth. Capital G is the gravitational constant. This is a physical constant. This does not change throughout the entire universe. It's a universal constant. So anytime you're doing this calculation, no matter what you're calculating the gravitational force between, you're always going to have to factor in the multiplication of 6.67 times 10 to the negative 11. And then that constant is multiplied by the mass of the first object times the mass of the second object, divided by the distance between those two objects squared. So you can see in the picture here, if we wanted to calculate the gravitational force between the Earth and the sun, we would maybe assign m1 to Earth, m2 to the sun, and then I would multiply the mass of the Earth times the mass of the sun, and then divide by the distance between the Earth and the sun squared. Probably the most common computational errors for this equation are forgetting to multiply by the gravitational constant, and then second is forgetting to square the distance in the bottom of that fraction. So this square right here, I recommend doing first, and I'll show you the procedure that I use for calculating this problem. But that's one of the things that's most commonly missed when calculating this equation. All right, and gravitational force, not listed on here, but it is a force, so it will be measured in newtons. All right, so before we do a full calculation for that gravitational force equation, we want to just remind you about scientific notation, because in this class today, in this chapter today, we're going to be talking about very, very large numbers. Things like the mass of the Earth and the mass of the sun. Those are obviously going to be extraordinarily, astronomically large numbers. We do not want to have to type out 6 with 24 zeros after it into our calculators. So we need to use scientific notation in order to have a more convenient way to write and type these numbers. So the way that we do that is we take this number and then we basically rewrite it. It's just a shorthand way of writing it as rewriting it as a multiplication or a product of a digit term and an exponent term. So the digit term is the number that's out in front. So with the mass of the Earth, we had 6 times 10 to the 20, 6 with 24 zeros after it. So our number out in front is just 6. And then we multiply that by 10 to some exponent. And in this case, it's 24 places, and it works out that that's 24 zeros. But note that this number is not the number of zeros. It's just the number of decimal places that you move the exponent. This exponent is positive, so that means that we're going to, if we were counting from 6.0, we would count 24 decimal places to the right in order to write this in the expanded form, and then fill in all those places that we counted with zeros. So a positive exponent in scientific notation indicates that this is a large number, a number that's larger than 1. In chapter 12, which we'll see later this week, we're going to be talking about atoms and subatomic particles. So we need a way to also conveniently write very, very small numbers like the mass of an electron. The mass of an electron is decimal point, 30 zeros, and then 91 after a kilogram. It's very, very small. We don't want to have to type this number into our calculator every time we need to calculate something with the mass of an electron. So we can more practically write this as, again, the product of a digit term and the exponent term. This time we have 9.1, and the standard form of scientific notation always has that decimal point after the first number. So I wouldn't write 91 times 10 to the negative 30, even though that technically would work out the same in the expanded form. You want to always put that decimal point right behind whatever that first number is. So 9.1 times 10 to the negative 31. And now note this time that the exponent is negative, so we're going to be moving that decimal point to the left. So we would count 31 places to the left and then fill in the places that don't have numbers before with zeros. So note that the 9 in this case is going to take up one of those spots, so I'm not going to have 31 zeros. I'm just going to have 30 because I had to count over the 9 for one of my places. So a negative exponent means I move the decimal point to the left to write it in its expanded form, and then that also indicates that this is going to be a fraction, a number smaller than 1. All right, so just for example of how we would convert these numbers into their expanded form from scientific notation, we have 8.32 times 10 to the 5th. The positive 5 in the exponent indicates that I move the decimal point 5 places, and then because it's positive, I move it to the right. We know that this number is going to be larger than 1. So I would just count 1, 2, 3, 4, 5. And again, note that the 3 and the 2 take up 2 of those places that I counted, so I only end up with 3 zeros at the end. So 8.32 times 10 to the 5th equals 832,000. And then for the next example, 4.15 times 10 to the negative 4, the negative 4 indicates that this number is going to be smaller than 1, and I'm moving the decimal point 4 places to the left. So I take my decimal point and count 1, 2, 3, 4. That leaves me with 3 zeros. 1 space is taken up by the 4, and I end up with 0.000415. These numbers are exactly the same as each other. It's just a different way to write it in order to make it more practical for calculations. So the way that you're going to type this into your calculator, I believe on the Mac calculator, if that's what you're using, there's a button that says EE on it instead of EXP, like this note in the middle here. But all the calculators are different. Unfortunately, they can't seem to agree. The calculator companies can't seem to find one standard way of writing scientific notation. So we'll show you a couple different ways here. So the way that you type this into your calculator that really shortens it for you is going to be if you had 3 times 10 to the second. All you have to do is type the digit term out in front. In this case, it's going to be 3, and then hit the exponent button, which is either going to be EXP or EE. And if it's not one of those two on the calculator that you're using, you can ask your instructor and they'll be more than happy to help you find that scientific notation key. So you just hit the digit term out in front, exponent, and then whatever that exponent is. So you don't have to worry about typing, hitting the multiplication key or writing in 10. When you hit EXP, that means times 10 to the, and then you just type in the exponent. And then if you do this on your calculator, and you can try it out now, if you hit 3, EXP, or EE, 2, then that will give you, it will show you 300 in this case. And then you can just treat that when you type that in as a normal number, multiply those numbers together, and you should be good to go. With a negative exponent, you have to be careful. It's pretty much the exact same process. You type the digit term out in front, the EXP button, or whatever your scientific notation key is, and then hit the exponent, but you don't want to hit -5. You don't want to hit the subtraction key. there should be something on your calculator that indicates positive or negative. So you want to hit the 5 and then hit the positive negative key, and that should give you a negative exponent. It should show up on the screen before you hit equals correctly. But play with that, and if you need any help, of course, ask now or ask your instructor later when you're doing these calculations. All right. Any questions so far? Okay, just give me 1 second. I'm going to get my my calculator up here, so hold on 1 second. Okay. Sorry about that. It's not letting me exit. So I was going to pull up the calculator to do this full calculation for you, but hopefully you can take it step by step. I'll show the calculation up here. But if you have any questions on how to input the calculation, you can let me know. All right, so this is example calculation calculating the gravitational force between the Earth and the Moon. So anytime you see the request to calculate for gravitational force, you know you're going to go to Newton's universal law of gravitation on your equation sheet. And I would definitely recommend writing this one out. It is a multi-step problem, and I don't recommend trying to do this in your head or simply just typing it into the calculator. I definitely encourage you to write it out. It's a little bit longer than usual. All right, so write out this equation, and then right off the bat, I want to remember that the gravitational constant is a physical constant and will always be 6.67 times 10 to the negative 11. So that g is a number that's already known. It's not something that's going to be given in the problem. So the mass of the Earth is given in the problem, 6 times 10 to the 24 kilograms. Mass of the Moon, a little bit smaller, 7 times 10 to the 22 kilograms. And then the distance between the Earth and the Moon is 3.84 times 10 to the 8th. And that's all the remaining information that I need to solve this problem. So here's what it looks like. And this is why I encourage you to write it out. Because especially with very large values, these things can get a little bit messy with all the scientific notation. But the important thing to remember is that these are just numbers, and it's just basic. These are just different ways to write numbers. So it just comes down to the basic procedures, algebraic procedures we've already been using. So the way that I like to do this is, first thing I like to do is simplify the fraction. So I take the mass of the first object times the mass of the second object, and then rewrite that top of the fraction as 4.2 times 10 to the 47. That was 6 times 10 to the 24 times 7 times 10 to the 22. And then I want to also put in its simplest form the bottom of the fraction, which is 3.84 times 10 to the 8th squared. And then I end up with 1.47 times 10 to the 17th. After that, this is just a simple fraction, so I want a simple division problem, so I will reduce that next. So I do 4.2 times 10 to the 47 divided by 1.47 times 10 to the 17th, and rewrite that. And then the last thing I have left to do is multiply times the gravitational constant, 6.67 times 10 to the negative 11. And then what I end up with is 1.9 times 10 to the 20th newtons. And that's my final answer. So hopefully you can type this into your calculator. You have this this presentation in PDF form. So maybe run through the examples before you submit the assessment and just make sure that you're getting the calculations correctly and getting these same final answers that we have shown on screen. It's a good method to check yourself before you submit the actual assignment. So this is a very large number, 1.9 times 10 to the 20th. The reason that this is such a large number is because the mass of the Earth and the mass of the Moon are very, very large values. Even though the distance between them is pretty far, the masses make up for it. Those masses are large enough to be able to create a substantial force between these two objects. Gravitational force is actually the weakest of the four fundamental forces in nature. If you've ever tripped and fallen to the surface of the Earth, it took the entire mass of the Earth to do that to you. But if you've ever had a sock stick to a shirt after coming out of the laundry by static cling, that force between the sock and the shirt is thousands of times greater than the gravitational force of the Earth. So the gravitational force is a relatively weak force, but with very, very large masses or over relatively short distances, it can be noticeable. And it can be the dominating force. And in fact, it is one of the dominating forces that we experience on Earth. So this relationship that I just referred to can be discussed in the terms of our proportionalities that we were introduced to on the very first day of class. Gravitational force is going to be directly proportional to both of the masses. So what that means is that the more mass, the more gravitational force. As we just said, it takes a lot of mass to be able to even notice the gravitational force. So they're directly proportional to both the masses. So what that means is that if you increase one mass by some factor, then the gravitational force is also going to increase by that same factor. So if I double one of the masses, I'm also going to double the gravitational force. What happens if I double both of the masses? If I double both the masses, is the gravitational force going to increase or decrease? Increase. Thank you, Stephen. Exactly right. It's going to increase. If you increase one mass, it goes up by a factor of 2. Do you know by how much it'll increase if I increase both masses by a factor of 2? 4. Perfect. It increases by a factor of 4 if you double both of the masses. It almost comes into like an exponential relationship because you have mass 1 times mass 2. If we're just looking at increasing both of those, then you end up with 2 times 2 on the top, and you end up with a gravitational force increased by a factor of 4. Very good. All right, so directly proportional to both the masses, but remember it's directly proportional only when you're individually referring to one of the masses. If you're referring to the distance, how that's related to the gravitational force, it is inversely and exponentially proportional to distance. So what that means is that when one value increases, the other value will decrease. The greater the distance between two objects, the less gravitational force will be experienced. Because of this square, then the amount by which the distance increases or decreases changes is going to have a much greater effect on the gravitational force. So if I increase my distance by a factor of 2, then my gravitational force is going to go down by an exponential amount, a factor of 2 squared, or 4. So if I move two objects twice as far away from each other, then the gravitational distance will go down by a factor of 4. And that's because this distance is in the bottom of the fraction and it's also squared. All right, so knowing that relationship, knowing that it takes a very large amount of mass in order to be able to even notice the gravitational force, let's do a calculation between two Earth-sized objects with Earth-sized distances between this businesswoman and this chef. They both look pretty thin, so we'll give them 50 kilograms each, and let's say they're 10 meters away from each other. Now remember that the universal law of gravitation is universal, so I can use the same equation to calculate the gravitational force between these two ladies as I could between the Earth and the Moon. So I'm going to rewrite my equation again, remembering that G is a physical constant, so I'm going to end up multiplying this equation by, or the things given in the problem to me, by 6.67 times 10 to the negative 11. This time, my equation looks a little bit more manageable because I don't have all that messy scientific notation in it. So I have 6.67 times 10 to the negative 11 times the two masses, 50 times 50, divided by 10 squared. Now, even though these numbers are smaller, I definitely recommend still reducing the fraction first. Do 2,500, 50 times 50, by multiplying the two masses together in the top of the fraction, divided by 10 squared in the bottom of the fraction, which is 100. And then I would multiply or divide 2,500 divided by 100, which will just give me 25, but I don't think I have that written in steps here. And then I multiply 25 times 6.67 times 10 to the negative 11, and I end up with 1.6 times 10 to the negative 9. So you can see, even though these two women are standing only 10 meters from each other, the gravitational attraction between smaller bodies, like 50 kilograms, like things that we find on Earth, is noticeable, or is not noticeable. It needs to have very large bodies in order for it to be noticeable. All right, any questions so far? All right. So this next concept is called the inverse square law. And the inverse square law is a concept that encompasses a couple of different topics that we're going to cover in this class. We're going to introduce the inverse square law today, but we're going to see it again when we talk about electricity. Then we'll see it again when we talk about magnetism, and again with sound, and again with light. So this inverse square law is not just specific to gravity, but it does apply to gravity. What the inverse square law says is that the intensity of something is proportional to 1 over the distance squared. And this is really just the same thing that I said on 2 slides ago, where we said that the gravitational force was inversely and exponentially proportional to distance. The greater the distance from an object, the less the gravitational force, and it's by a factor of an exponent. So it's exponentially less the further two objects are moved away from each other. So what this law says is just, it kind of makes it a little more generic. It says the intensity of something is proportional to 1 over the distance squared. And in this case, that intensity is going to be referred to how intense the gravitational force is. That little alpha symbol that looks like it's in place of the equal sign is proportional to. So that just means that we've taken out all the other factors, the gravitational constant, the m1 and the m2, and we're just looking at the relationship between intensity and distance. One important thing to note is that no matter how great the distance, gravity will approach, but it will never reach 0. By mathematics, this distance can get as large as it wants, but it's still going to be there's still going to be some 0.000. You can have a million zeros, but there might still be a 1 at the end of those zeros. So it can be a very, very small number that we would never be able to notice the effects of the gravitational force, but every object in the universe with mass has some effect on every other object in the universe because of this fact that it can never reach 0. So you have an effect on Pluto, and Pluto has an effect on you. All right, so this is just what if you were to plot the force versus distance, it would come out in this curved shape because of that exponential. It drops off at a greater rate than just a directly or inversely proportional line, which would be straight. if we start with an apple on Earth and it weighs 1 Newton, if we take it twice as far away, it'll weigh a quarter of a Newton because the gravitational force has decreased because we've moved it further away, and it will decrease by a factor of 2 squared or 4. So it's a quarter of what it was. If you move it 4 times further away, then the apple will weigh 1 over 4 squared, which is 1 over 16. So it'll weigh 1/16 of a Newton here. Gravitational force is proportional to 1 over the distance squared. This symbol, that little squiggly line, that means it's approximately, which is not really the correct symbol. It should be that alpha symbol, which is D is proportional to. Yeah, this means approximately or is similar to. Oh, the one on the last slide, that's the correct one. This is the alpha symbol. It means is proportional to. Good question. Yeah, so it kind of takes place of the equal sign because we know that the gravitational force isn't exactly equal to 1 over the distance squared. It's just proportional to 1 over the distance squared. So remember, our equation is g m1 m2 divided by distance squared, and then we can add the equal sign. But if we're just comparing the gravitational force and the distance squared, and we want to know how they're related to each other, we keep all these other things constant, so we can just kind of ignore them. And so that's where the proportionality comes from. So you can change it to proportional when you take all of these and set them to 1. And then you end up with 1 over the distance squared. Yeah, I like that. That defines it pretty much in the area. But what it means is that if you did 1 over the distance squared, there would be some number that you could multiply it by to get to the gravitational force. That's what proportionality means. Good question. Thank you. All right. Get back to where it was. Okay. So, couple more topics, weight and weightlessness. We were introduced to weight in the very first class. We remember that weight and mass are 2 different things in physics. Mass is going to be the amount of matter that your body contains, and the weight is the force that is exerted downward by your mass because gravity is pulling you down. So force exerted against a supporting floor or weighing scale due to gravity. When you stand on a scale, it's measuring your weight, not your mass. If you went to another planet and stood on a scale, it would read something different because the gravity would be pulling you down at a different rate. So the reason that I have Superman here is because one of the explanations, the origin stories for Superman's super strength is because he grew up on a planet that was about the same size as Earth, but much, much more dense. So it had a lot more mass. And if you have more mass, as we know by Newton's universal law of gravitation, it has more gravitational force, and that acceleration of gravity is going to be greater. So when he was there, his muscles, and he was born so that he had to constantly overcome the gravitational force of this planet in order to lift things. And then when he came down to Earth, everything seemed super easy to lift because the gravity was only 9.8 meters per second squared. So it's kind of like how you would feel like a superhero if you went to the moon, because you could jump off high buildings and lift things and throw things further, because the gravitational force on the moon is going to be much less. Doesn't really explain why it can fly, but other than that, it explains the super strength. So the only reason that I mention weight again is because it's often thought that weightlessness, which is the term that we're really referring to in this chapter, is the way the word sounds. It sounds like it should be an absence of weight. And that's not what it is. Weightlessness is not you losing weight. Weightlessness is more of a sensation. It's simply a condition where a support force is lacking, like when you're in free fall. So if you've ever been on a roller coaster and you go up to the very top and you're momentarily lifted out of your seat, you feel weightless. You get this sensation of being weightless. Or if you've ever maybe done bungee jumping or those small scale bungee jumps at amusement parks, at first, right when you jump off, before air resistance can have real effect on you, you feel the sensation of being weightless because gravity is the only thing that's acting on you, like in free fall. And a support force is when something is touching you. So we know that the only reason we feel gravity at all is because of these outside forces. We feel gravity when we're standing on the ground because of the support force of the ground. We feel gravity when we're falling because of air resistance. But if we didn't have air resistance or the ground or some sort of support force, then we would not feel like we were falling. We would not be able to feel gravity if we closed our eyes and fell and didn't have any other outside forces. We wouldn't be able to feel gravity. The only reason we feel gravity is because of outside forces. So in that case, we would feel weightless. We would feel like we didn't have any weight because there was no support force to tell us that we did. This is the reason that you can see here that we have pictures of the zero gravity simulator, and then also a pretty entertaining YouTube video, which is cats in zero gravity simulator. They keep trying to land on their feet, so they just kind of keep flipping. It's a little mean, but it is interesting. Anyway, sorry, sidetrack. The shuttle astronauts feel a sensation of weightlessness. If you've ever, watched a movie about people out on the space station, or seen any video of the astronauts out in space, you see that they kind of float around, and they can, they kind of move through space differently than obviously we do on Earth. And the reason for that, the reason that they feel this sensation of weightlessness, is not because gravity is less at the space station. It is less, but it's only about 11% less than it is on the surface of the Earth. So if you took a scale and stood on the surface of the Earth and you weighed, let's just say 100 newtons, and then you went up to the height at which most of the manned space missions travel, you would weigh 89 newtons. So gravity would still have a really large effect on you, just because you're not that far away from the Earth that you're not experiencing that anymore. The reason that all these astronauts feel weightlessness is because they're actually constantly in a state of free fall. They have a sideways velocity that's tangent to the surface of the Earth that makes them move fast enough sideways that as they move sideways, they're constantly falling, but they're matching the curvature of the Earth as it rotates away from it. So they're actually constantly falling, which is why they feel weightlessness, but they never actually hit the ground because they're moving sideways fast enough so that they don't actually, they match the curvature of the Earth. If something stopped their sideways velocity and made them slow down, then gravitational force would bring them down towards the surface of the Earth and they would come crashing down. So the reason that you feel weightlessness is because in space is because of they're constantly in a state of free fall. And that's what these zero gravity simulators do. You take a plane up to a certain height, and then they just drop you down for a certain amount of time. So you're in a state of free fall, and then you feel weightlessness. This is actually a pretty famous experiment, which seems pretty simplistic, but yeah, exactly. Edward, parabolic flights. That's exactly what they do for that process as well. If you remember, a scale just measures your support force. It measures the balancing force to balance your weight downward. So if you stood in an elevator and it was not accelerating up or down, the scale would read your normal weight. But if it accelerated upward, that would cause an increase in the force downward on the scale, so it would show greater than your normal weight. And then if you were accelerating downward, that would kind of lift you up off of that scale just a little bit, and it would read less than your normal weight. And then, of course, I don't think this was actually part of the experiment, but if the cable snapped, then the elevator, and the scale would all accelerate towards the surface of the Earth in free fall at 9.8 meters per second squared, and you would experience that weightlessness, zero weight. All right, so next topic is projectile motion. And a projectile is any object that moves through the air or through space solely under the influence of gravity. Now, this is going to sound similar to our definition of free fall, and there's a good reason for that because these objects are considered in free fall. The difference is that you're going to have an initial launch speed and an initial launch angle. So the objects are not just going to be dropped like they were before in free fall, but they're going to be launched, and then they'll take a curved path, which we'll discuss a little bit more in just a second. But it's important to note that an object that is just dropped is also considered a projectile, even though it doesn't have an initial launch angle. If it's just dropped, still considered a projectile because it's moving through aerospace solely under the influence of gravity. All right, so let's take a close look at this picture and look at the different components of the motion. So we have two different components that we're concerned with projectile motion. We have the horizontal component, which is the side-to-side motion, how much that object moves side to side per unit time. Let's just say every single second. We want to know how much that object has moved horizontally. And then we also have the vertical component, which is the object that, how much the object moves up and down. So with a projectile, the only thing that's acting on the object is gravity. So gravity is always a vertical force. It always acts right down towards the surface of the Earth. So the only force acting on this object is vertical. And remember, forces cause accelerations. So the only way that this object is accelerating is down in the vertical direction. So if we look at where this ball is every single second, let's assume that every time we freeze frame the path of this ball in this picture, 1 second has passed. So after 1 second, it's moved this short distance from where it was launched down to a lower height. After 1 more second, it's moved a greater distance because gravity is pulling it down and it's accelerating, it's moving at a faster speed. And then after another second, that distance increases again. And after another second, that distance increases again because it's constantly accelerating. In the horizontal direction, there's no forces acting in the horizontal direction. Gravity is the only force, and gravity acts exclusively downward in the vertical direction. So if there's no forces in the horizontal direction, that means that there can be no acceleration. So the motion in the horizontal direction has to be constant. So if we look at how far this object has traveled horizontally after 1 second, it's going to be the same distance as the object has traveled horizontally after 2 seconds, and 3 seconds, and 4 seconds. All of these distances are going to be the same because the horizontal component remains constant because there are no forces in the horizontal direction. So the vector sum, or the combination of these of the horizontal and vertical components, adds up to the true path that this object takes, which is a parabola or parabolic path. This is the shape of the curved path of the projectile. So in summary, the definition of projectile motion is that it's a combination of a constant horizontal component and an accelerating vertical component due to gravity. And then the sum of those two components gives you a parabolic path, which is the true path of the projectile. Yes, John, that's an excellent question. Wouldn't you push on the ball to throw it via force? Initially, yes, but as soon as it's in flight, the only thing acting on it is going to be gravity. So that initial launch, at that moment of launch, it's not going to be in true free fall or a true projectile because gravity isn't the only thing that's acting on it because your hand has acted on it. But after it's in flight, then the only thing acting on it is gravity. Excellent question. All right, so we could ask you a couple different questions about this. An object at the edge of a cliff is shot horizontally with a speed of 10 meters per second. Assuming no air resistance, if the object is still in flight, what is its horizontal speed 4 seconds after it is shot? This is typically a very, not a difficult question, but one that gets mixed up because it looks like it should be a calculation. We give you all these values and then ask for a speed. So it looks like it should be an equation. But the key word here is horizontal speed. If the horizontal component of a projectile is constant, then what's its horizontal speed 4 seconds after it's shot, if its initial speed was 10 meters per second? Perfect, 10 meters per second. And then after 9 seconds, also 10 meters per second. The horizontal component is going to always remain the same. So if you see these words, horizontal speed, it doesn't matter how long it's falling, if it's 4 seconds, 9 seconds, a million seconds, if it's still in flight and still gravity is the only force acting on that object, then the horizontal speed is going to remain the same. So it's not a calculation, it's just the same as it was the initial speed. What will be a calculation is if we ask you to solve for the vertical speed. The vertical speed is going to be affected by gravity, so it's going to be accelerating. So in this case, it's not going to matter. Again, this is extraneous information for this one. For horizontal speed, that was the only information we needed. For vertical speed, it doesn't matter how fast it was traveling originally, because all we're concerned with is how much gravity has acted on it after it's in flight. So because its vertical speed only depends on gravity and time, so the only thing we're really concerned with is how long has it been falling. And the vertical speed will be measured by multiplying gravity times time, which is really just a rearranging of the acceleration equation that we saw on the very first day of class, or the very first chapter. So we end up with 9.8 times 2, and it's 19.6 meters per second. So the vertical speed will change, but the horizontal will not. All right. So, of course, you'll get to play with this with the simulation. That's what you do this week. But for equal launch speeds, we have different, the same range is obtained for two different projection angles. The range is going to be the distance from where the object was launched to where the object hits. So the distance it traveled horizontally along the ground. It doesn't matter the path that it took. The range is where it ends up. So for complementary angles, and these are going to be any two angles that add up to 90 degrees, the same range will be achieved. So if this is good strategy for Angry Birds, which is why I have this on here. If we take the angry red bird and we launch him, we want to get over something that's in our way here to get to the pig, and we launch it at 75 degrees, we can hit that same pig if we launch it at the complement of 75 degrees, which is 15 degrees. 75 plus 15 equals 90. So if you launch it at 15 degrees, it will hit the same pig. It will end up at the same spot. So it'll take two different paths, obviously. One will go a lot higher, one will go lower, but they'll end up in the same spot. 60 and 30 will both end up at the same range because 60 plus 30 equals 90. And for maximum range, for the longest distance, which you would probably know if you were playing Angry Birds and you launched it, you needed to hit something that was really far away, your subconscious would tell you to launch this at 45 degrees. But the reason that you want to launch it at 45 degrees is because 45 plus 45 equals 90. So 45 is a complement of itself. So 45 will give you its maximum range. All right, so any projectile that has a sideways speed that's moving fast enough to fall continuously around the Earth is going to be called a satellite. And that's exactly what I was talking about with the space shuttle that has to move at a certain speed sideways to match the curvature of the Earth as it rotates away from it. So it must be moving at a certain number. It's actually 8,000 meters per second. For the space shuttle, this is fast enough to orbit the Earth every 90 minutes and fast enough to see 16 sunrises and sunsets every single day, every single 24-hour period. I just watched the movie Gravity, and they had all that debris coming at them, and they would set their watches for 90 minutes because that's how fast that's how long it took for the debris to orbit around the Earth once, and then it was going to come back and hit them again every 90 minutes. All right, so because the Earth's curvature drops a vertical distance of 5 meters for each 8,000 meters tangent to the surface, the minimum speed a projectile must have to orbit the Earth is 8,000 meters per second. This again is, sometimes it looks like a calculation because we're going to, if we asked you something like this on the assessment, we would ask you for the speed a projectile must travel. And looks like it might be a calculation, but again, this is just a number to know. Of course, you can look it up, but it is 8,000 meters per second. The moon is our own natural satellite. It has to travel at a certain speed in order to maintain a tangential speed, in order to maintain a sideways velocity that is enough to not have the moon and the Earth come crashing down towards each other. We know that they're attracted by gravitational force, but it has to have this initial speed sideways in order to maintain orbit and not just come crashing down into us. Edward, I've actually had that suggestion play Kerbal Space Program. I've been meaning to check that out, and I definitely will. Apparently it has very good astronomy and physics in it, which would be cool. Probably very bad jet lag. Astronomers have a lot of astronauts have a lot of problems with traveling out in space. Probably jet lag is going to be one of them, in addition to weakened muscles and bone structure and all that kind of stuff. Very hard on the human body. There's a whole field called astrobiology where astrobiology deals with life out in space, but then there's another aspect of it that deals with the biology of humans under microgravity conditions like that. And it's pretty substantial over a certain period of time. All right, so orbit is really just, it's the constant battle between an object's inertia, which wants it to keep moving in the same, moving in the direction that it was moving before. Inertia and object in motion wants to stay in motion in the same line and at the same speed. So its inertia wants to pull it away at that tangential velocity in this direction of this blue arrow, and gravity wants to pull it down towards the surface of the Earth in an arrow that would be this way. The combination of the velocity vector of the object's inertia and the gravitational force is orbit. The combination of those two forces gives you that almost circular path that we call orbit. We have a lot of useful satellites up in space. We have the GPS systems, we have cell phone satellites, spy satellites, all sorts of useful satellites, functioning satellites up in space. Total, there are only about 800 that are currently functioning. If you add up all the debris, all the non-functioning satellites, all the pieces, the junk that astronauts have left behind, it totals about 30,000. Man-made satellites that are actually orbiting the Earth, and not all of them are functional at all, just stuff that we've left up there. This is a picture from NASA's website that shows each of these. All of these individual dots are debris that we have left behind. This is the low Earth orbit view, and then even more alarming is the high Earth orbit view. So if you think we're bad at littering on Earth, we're really bad at littering in space as well. These things look like they should be crashing into each other all the time. Fortunately, the Earth is large enough that this scale is a little deceiving because these objects are not actually that close to each other. They are still relatively far apart, but occasionally you do have collisions between debris in space. And if we keep sending more stuff up there, then we'll keep getting more and more, and those collisions will become more commonplace. Of course, some of the debris, smaller debris, will lose its momentum and end up burning up in our atmosphere. But it seems like we can't keep up with all that stuff. So this is the image of all the space debris. All right, two more important numbers to remember in addition to the minimum speed to orbit the Earth. The escape speed is the initial speed that an object must reach in order to escape gravitational influence of Earth or another celestial body. The escape speed depends on the mass and size of the object. So specifically for Earth, the escape speed is going to be 11,200 meters per second. That is the speed that you need in order to be able to get away from Earth and move outward into the rest of our solar system. If you don't go faster than that, you'll either come crashing down towards the surface of the Earth, or you'll end up in orbit. In order to actually escape, you need to travel 11,200 meters per second at a minimum. And then in order to escape the solar system, which is really just in order to escape the sun, because the sun is, again, 98 to 99% of the mass of the solar system, that speed increases to 42,500 meters per second. Yeah, that's a really good question, John. Does the speed of the moon change when it slingshots around the Earth? So like when it's closer and then pulls away. The moon has a close to circular orbit, but it's not exactly circular. It is slightly elliptical, like most of the planets. So it does, at some point, approach Earth at a closer distance than at other points in its orbit. This position, when it's closest to Earth, is called perihelion, and then when it's farthest from Earth, is called aphelion. At perihelion, that's when the moon is moving the fastest. So it does increase its speed when it's closest to the Earth because gravitational force is greater with decreasing distance, and then it's slowest when it's farther away. And that the same goes for all the planets as well. Good question. All right, so if we were to match each of the orbits with one of the following speeds, the first one is 11,200 meters per second. You can go ahead and type your guess, A, B, C, or D, about which path an object would take if it was moving at 11,200 meters per second. Perfect, you guys got it. C, 11,200, this is the minimum distance to escape Earth. So it would escape orbit and escape being pulled back down by the gravitational force of the Earth. 8,000 meters per second, which one would that be? Good, excellent. So 8,000 meters per second is going to be A, because that is the minimum speed that an object needs in order to maintain orbit. At the minimum speed, that's going to bring you to almost a completely circular orbit around the Earth. And then I'm going to jump down because I think you guys have the hang of it here, but 9,000 meters per second is going to be in between the minimum speed to orbit and the minimum speed to escape. So it's not going to quite escape, but it's going to start to think like it's going to be able to, and it's going to start to pull away, and then it's going to come back closer again. So this, when you travel in between 8,000 and 11,200, you're going to orbit, and the closer you get to 11,200, the more elliptical the orbit will be. And then lastly, I guess I could show the answers here, C, A, D, and then the last one is, number 3 is going to be D, because this is 42,500 meters per second. That would be plenty to get away from the gravitational force of the Earth. And in fact, that's enough to escape the gravitational pull of the sun or the solar system, either way you want to say that. All right, so that is the end of the Chapter 4 lecture. Thank you guys for sticking around for a couple more minutes. I apologize I went over time. If you guys have any questions, I will stick around for a couple more minutes. But if not, you are free to go. And I thank you for coming and hope to see you next time. I stop the recording real fast and then I will answer all the questions.